All right, open up your book to section 11-3. We're on page 574 in your book. This section is titled Intersections of Polar Curves, and the objective here is given two polar equations, find the solutions to the system of equations, and relate them to the intersections of polar curves. So we're trying to find intersections is what we're trying to find. To help us understand how we find intersections, let's relate what we know about Cartesian and compare or contrast that with what happens with polar. So that's where we're going to start. Let's start with Cartesian. So the first thing to note here, first of all, if you're trying to find intersections of Cartesian coordinates, we're talking about given two Cartesian equations, and you're trying to find the intersections. It turns out that the point xy is going to be an intersection if both equations contain that point xy. And I hope that at this point that seems obvious to us. That if you're going to claim that you've got two functions, you're looking at them, maybe it's a linear function and a quadratic function, and you found an intersection, that if you're saying that at x equals 1 there's an intersection, then the y values of those two graphs better be the same at that point. Again, I think at this point that should be pretty obvious to us about Cartesian. The second thing that it should be obvious to us when we look at these graphically, that the graphs of these two Cartesian equations will actually cross, or at least touch each other, at this point xy. When you look at the graphs, you're going to actually see an intersection because you can see they cross or touch each other at that particular point. And the third thing that hopefully again is obvious to us from Cartesian is that the graphs will not cross at any other points. You're not going to find any other intersection out there other than these ones where the x and y values are the same between the two equations. No other points is that going to happen. Let's compare that then with polar coordinates. And I'm going to kind of go through this and compare these side by side, or I guess top to bottom here is really what's going to show up here. But let's compare what we know about polar coordinates then. If we're trying to find intersections in polar coordinates, again, given two equations of two polar equations, the first thing to note, and I'm going to kind of try to keep these together so you can see the Cartesian at the top of the page and the polar at the bottom of the page. The first thing to consider here is that the point r theta is an intersection if both equations contain the point r theta. Again, that should be pretty obvious to us from what we already know about Cartesian, but I do want to make sure we're clear on this, that it might not be obvious, that it is possible that there may be other places where these intersect where the r theta values are not the same. And the reason for that, we will see, is because with Cartesian coordinate system, when I give you a point xy, that defines a unique point. There's no other point in the coordinate system that has that name, and there's only one spot that has that name. It's unique. That's not true when we jumped over to polar. That's what we saw in the last section. That when you marked a point r theta, there was actually an infinite number of names you could use for that particular point. I could change the r value from being positive to negative, or I could add coterminal angles onto that angle theta and come up with more names for it. But again, the only way that I have an intersection is that the r and theta value have to be the exact same on both curves. If the r value is negative on one and positive on the other, that's not an intersection, is what we're saying here. R and theta have to be identical. Again, that's taking from up above what we already know about Cartesian. The second point to make is that when you look at these graphically, the graphs will actually cross at the point r theta. Again, from what we know about Cartesian, that hopefully makes sense to us, that if I see an intersection there in Cartesian, I know that means that x and y must be the same. When I look at these in terms of polar, though, just because the graphs cross won't necessarily mean that the r and theta value are the same. But I am guaranteed that if it is an intersection, that the graphs will actually cross at that point r theta when it is a true intersection. And here's the one thing that's a little bit different and perhaps a little bit odd to us here because we have not seen this before with Cartesian. When you look at a polar graph and you're looking for those intersections, you may find that your graphs actually cross at other locations in which r and theta are not the same. And these are what we call false intersections. These are those places where the r values are the opposite, or the theta values differ by a multiple of 360 or something like that. Those are the false intersections we're going to find. All right, so what exactly is a false intersection? Well, let's define that here. A false intersection is a point where the polar graphs appear to intersect but do not have the same r theta values at that location. False intersection. If you trace one graph to that particular value of r theta and then trace the other graph to that particular point, you'll find that it has a different set of values for r and theta. This is exactly what it means to be a false intersection. Graphically, it looks like they intersect, but when I investigate algebraically and look at the values of r and theta, they're not the same, so therefore it is not an intersection. And we're going to call those false intersections. I guess the last question that you might have is, well, where do these false intersections occur? Well, they occur in these exact locations that we talked about in the last section when we talked about the number of different names that you can give to a particular point in polar coordinates. We said it was infinite. And what are those different names that you could pick? Well, here we go. This is the same thing we had on that slide in that first section. R theta might be a point on one curve, but it could be on the other curve that it's r and then theta plus some multiple of 360. In other words, it's a coterminal angle with it. The r values turn out to be the same, but the theta values are not the same. Thus, it is not an intersection. Or it could be the case that these are in opposite quadrants here. So r theta could be a point on one curve, but then when I jump over to the other curve, it could be the opposite of r and theta plus 180, and plus some coterminal angle to that even. Could be the point on the other curve. And again, notice that the r values are definitely not the same here, and the theta values are definitely not the same. So these cannot be intersections then. These are where our false intersections are going to occur, when these types of things happen. All right, so let's take a look at an example. Look at example 1 there on page 575 in your book there. It says to find the solution to the system consisting of the limosone, r is equal to 3 plus 2 cosine of theta, and the 4 leaved rows, r is equal to 5 sine of 2 theta, in the domain from 0 to 360. All right, well, let's write down the two equations that they've given us here. We're going to sketch these in just a minute. Let's write down our equations here. They gave us that r1 is equal to 3 plus 2 cosine of theta. And again, hopefully we're getting better and better at recognizing what type of graph these are. They told you in this problem, but hopefully we recognize that's the equation of a limosone now. And we know a little bit about what that sketch should look like. And then the second equation, r2 is equal to 5 times the sine of 2 theta. And again, hopefully we're getting better at recognizing what that is. That turns out to be a 4 leaved rows. Now you might look at that and say, wait a minute, that's got a 2 there. Shouldn't that be, it's a 2 theta, shouldn't that be 2? Well, it turns out if that number is even, we end up with twice that many leaves. If it's odd, we end up with that same number of leaves. So that's why this is actually a 4 leaved rows here, okay? But let's go ahead and sketch that just to verify that's the case. I should also indicate we're talking about theta from 0 to 360. So we'll do this in degrees. So go ahead and grab your calculator and let's punch this into your calculator. All right, so go ahead and make sure you're in polar mode. Make sure you're in degree mode as well on your calculator. And as long as you are, then we can punch in these two equations here. You've got 3 plus 2 times the cosine of theta. And the second equation there is 5 sine of 2 theta. All right, so get both of those punched in there. Check your window to see that you've got a window we can sketch this in. 0 to 360 with a theta step of 5. That should be fine for us. And negative 10 to 10, that should be an okay window there for us to see this in. Actually, we probably could zoom in here a little bit. Maybe I'll do that in the X and Y direction. I think if we change our window, say to go from negative 6 to 6 for both the X's and the Y's, that'll give us a better sketch of this. Let's go ahead and graph that. And there we go. As that came in there, we can kind of count how many intersections it looks like we have here. Looks like there's 2 intersections I see over there in the first quadrant. There's 2, one really close to that x-axis there, but it looks like there's 2 in the second quadrant, 2 in the third, and 2 in the fourth, looks like. So it looks like there's a total of 8 intersections here. Again, graphically, that's what it looks like. We already know now that some of these are going to be true intersections, some of these are going to be false intersections. Let me grab a picture of this, and we'll put it into our work here. And I'm going to go ahead and make this a little bit bigger so I can actually mark which ones are the intersections here as we work on this problem. But let's go back to the calculator here, and let's change one thing here on how we graph this. If you go to your mode, you have this option down here that's sequential or simultaneous. Let's switch this over to simultaneous. That way, as it sketches it, it'll show me both those graphs at the same time. I'm not sure if I'm going to be able to pause this as it graphs. You'll be able to press enter though as it's sketching, and then you'll be able to see when those 2 graphs actually are intersecting each other. Okay. Again, I'm not sure if I can quite do that as it tries to graph this. I'm going to try that here on this calculator. But if we just go ahead and hit graph, yeah, that went way too fast for me to even stop it here. But yours, you can pause that as it graphs there. And as it pauses it, you should notice that as it goes through that first quadrant, that those 2 solutions you see there in the first quadrant are actual intersections. But you should notice that as it goes into the second quadrant, that row is all of a sudden, instead of being in the second quadrant, it jumps over to the fourth quadrant. So the second and fourth quadrants are not actual intersections. All right, so if we go back to our sketch here, again, I apologize that I can't slow mine down enough to actually show you these, but on your sketch there, you can mark which ones are the true intersections here. We should have been able to see that you have a true intersection right here, another one right here. Again, the 2 that you saw in the fourth quadrant, or excuse me, in the second quadrant were not. There's one in the third quadrant. This one's hard to sketch, just that one, but make sure you're marking that it's only the one in the third quadrant, not the one, don't include the one that's also in the second quadrant. And then this solution right here is also a true intersection there. So now the question is, well, what are those 4 intersections? Well, ideally, we could take our calculator, and let me jump back over here for a minute. We could take our calculator and we could go to our calc menu and we could actually find intersections. If I go to second calc, I'd like to be able to find intersections. But again, this is the problem of working in polar mode, is that you are restricted on what your options are that are available to you. I can't actually find intersections in here. So how are we going to do that? Well, this is where the auxiliary Cartesian equation comes in handy for us. So we're going to jump out of polar mode and we're going to switch over to function mode. So do that on your calculator. Change the mode. Back over to function mode. I'm going to get rid of simultaneous. I won't need that for the sake of what I'm doing now, but if you want to keep it sketching simultaneously, you can. And now in your y equals menu, let's put these 2 equations, 3 plus 2 times the cosine of x, again replacing theta with x and r with y, and do the same with the second equation, 5 times the sine of 2x. And there's our 2 equations there. Set up your window. Again, we're looking to go from 0 to 360, so set up your window that way. A scale of about 20 here should be fine. Our y's will be fine there from negative 6 to 6. Okay, and go ahead and graph that. And there we go. Now I can actually see the 4 intersections there. The other 4 false intersections that I was seeing, I can see that the graphs in those 2 quadrants, that is from 90 to 180, one is positive, the other one's negative. They're not actually intersecting there. And the same is true down there at the end. Okay, so I can see my 4 true intersections here. In fact, I'm going to go ahead and snap a picture of this and put it in there just so we remember that the auxiliary Cartesian equation is the way that we want to solve this problem here. All right. And now let's go ahead and find our 4 solutions here. All right, so to find your intersections, all we got to do is use the calc menu to do that. If you press second calc, this under function mode does have an intersect feature. So I can give it a first curve is I'll just press enter on y1, second curve I'll press enter on y2, and it looks like that first solution is somewhere around 40 degrees. So I'm just going to type in 40. You can trace back there and do the same thing. And I get this first intersection is at 34.263 and 4.652, or 3 I guess if we round that last digit. Now remember, when we write this in polar coordinates, we write it in the form of r theta. Theta is the x value for us, and r is the y value. So we write the y value first when we write this out, and then the theta value. All right. By the way, when you do this, this is actually storing those values that it just came up with into x and y for you. When it displays it on the screen, it actually did change those values for you. So because of that fact, and I've got 4 of these to do here, I'm just going to gather this data and I'm going to dump it into a list. So I'm going to just go into a list here. You could just write down yours, but since I'm going to do this all in the calculator and then put it onto the slide here, I'm going to store these into list 1 and list 2. And I'm going to store it in the order of r and then theta. So my y value goes in list 1, and my corresponding x value, I'll just type in x, goes into list 2. So there's my first 2 points there. Or sorry, that's my first point, my first r theta value. All right, let's go back to the graph and let's find the next intersection. So second calc, and we'll intersect the 2 functions there. Looks like the next one's somewhere around 60 degrees. I'm just looking at my tick marks, by the way, down on my x-axis to approximate where those are at. And so there's our next point. Again, those are stored now to x and y, so I'm going to go back to my list, and I'm going to add those onto my list here. So again, I'm putting the y value in list 1. Again, that's my r value. And then I'm going to put my x value, that's my theta value, into list 2. And that way I will hopefully not get these mixed up there when I go to write these out as ordered pairs. And let's go back to the graph. I'm going to find the next intersection. And I'll just choose the 2 curves there. It looks like the next intersection is occurring at somewhere around 180 there. I'm just counting out the tick marks there, so I'll say 180. Might actually be closer to 190, 185. Okay, so there's our next intersection. And again, let's take those values and put them into my list here. Go to Stat, Edit. And again, in list 1, I'm putting the y value. That's my r value. And in list 2, I'm putting my theta value. That's my x value. All right, one more intersection to find, and then I've got all of these. So go back to your graph. We'll find the intersection and pick your 2 curves. Looks like the next one's somewhere around 260. So I'll just type in 260 again. You can just use your arrow keys and trace over there. That's fine. So 255 is where that one's at. And we'll dump that into the last value here in our list. So again, I'm dumping in the y value into list 1. And I'm going to dump in the x value, that's my theta value, into list 2. All right, and now I should be able to grab a picture of this. And this way I have all these values all at once. And I can come in here and I can paste that picture for all of my solutions here. All right. And then I can write these down as ordered pairs here. I'm going to first write down the equation that I'm actually solving here, which is what you should do as well. I'm actually taking these 2 equations and setting them equal to each other is really what I'm trying to do. So the first equation was 3 plus 2 cosine of theta. 3 plus 2 cosine of theta. And you're setting that equal to the second equation, which was 5 times the sine of 2 theta. And then we solved to find the 4 solutions we end up with in the interval from 0 to 360. They are listed over in my table, but I'm going to go ahead and write these down as r theta values. So the R value is 4.652. I'm just going to truncate these for the sake of this example. 65. Actually, I'm going to round it. 653, and then the corresponding theta value there is 34.263. I'm going to put a degree mark on there just so I recognize that's the theta value. And the next one, 3.851 and 64.813. And again, that's degrees. And the last one is, or sorry, the third one is 1.010. And then it's 185.83. I think I need to get that value there off of that. Let me go back to my, need a third decimal here. So let me go back to my equation, or go back to my table here. It should be 8. Oh, it's already rounded it for me, so it should be 829 is what it should be. And I guess while I'm here, I'll get the last one. It should be 095. So this one was 829. So I'll erase that actually, 829. And the last one, let me just grab that off the table here again. Oops. Again, that's 095 is the 3 digits that I want there, 095. So the R value is 2.486, and the theta value is 255.095 degrees. All right, there we go. That's what they wanted. Find the solutions to that system consisting of those two functions are in that particular interval.